Today we want to introduce the study of some new polynomials in the channel. In this case, this is an important topic in special functions, and today what we are going to look is the Legendre polynomials. Okay, so we are going to start from the definition that the mathematician Rodrigues gave in the 19th century. He said that the Legendre polynomials can be expressed with this definition, where the nth Legendre polynomial p of x is going to be 1 over 2 to the n times n factorial times the nth derivative with respect to x of x squared minus 1 raised to the n power. Okay, so this will be like just the definition, and we may be interested in calculating some terms of the Legendre polynomials. For example, the zeroth Legendre polynomial of x is going to be 1 over 2 to the 0 power times 0 factorial, and the zeroth derivative with respect to x of x squared minus 1 to the 0 power. This is just going to be 1, and remember that taking the zeroth derivative is just like doing nothing to the function. Okay, so if we take the zeroth derivative of 1, we are just going to get 1, and of course this is also 1, so this is 1, and this is the p0 of x term. Okay, so this will be like the first Legendre polynomial for n equals 0. So for example, p1 of x is going to be 1 over 2 to the first power times 1 factorial, and then the derivative with respect to x of x squared minus 1. Okay, so this is 1/2 times the derivative with respect to x of this, which is going to be 2x. So we get x for the p1 of x term. Okay, let's do another try for p2 of x. This is going to be 1 over 2 to the second power times 2 factorial, and the second derivative with respect to x of x squared minus 1 to the second power. Okay, remember that this is raised to the n power. Okay, so we are going to get that this is 1 over 4 times 2, it will be 1 over 8, and then the second derivative with respect to x of x to the fourth minus 2x squared plus 1, and this is 1 over 8 times, what happens if we take two derivatives in this expression? We are going to get 4x cubed, then 12x to the second power, and then minus 4. Okay, so this is going to be 3 over 2x squared minus 1/2. We can say now that p2 of x is going to be 1/2 of 3x squared minus 1. Okay, so if we would like to calculate more terms for the Legendre polynomials, we just need to take n equals to 3, to 4, and so on and so forth. But we are going to stop this step right now. Another thing that will be very interesting about Legendre polynomials is that, look here, that we have a sum of two terms raised to the n power, x squared plus minus 1. Okay, so we know that there is a very famous formula for a sum that is raised to a power, known as the binomial formula from Newton. And the binomial formula says that we can express this, what we have here, as a sum from n equals 0, for k equals 0 to infinity of n choose k times, the first term, which is x squared raised to the kth power, and then -1 to the n minus k. Okay, so we are going to rewrite the expression of the Legendre polynomials in terms of the sum. So we are going to get that Pn of x is going to be equal to 1 over 2 to the n times n factorial times the derivative, the nth derivative with respect to x of the sum from k equals 0 to infinity of n choose k times x squared to the kth power times negative 1 to the n minus k power. Okay, so looking at the derivative is with respect to x and this sum is for k, well, we can just take this derivative into the sum. So there is no problem if we do that. And we are going to get the next 1 over 2 to the n factorial times the sum from k equals 0 to infinity of n choose k times negative 1 n to the minus k power, and then the nth derivative with respect to x of x, and we are going to multiply this. This will be x to the 2k power. Okay, so let's examine this term that we have here. We have an nth derivative with respect to x of a power of x. What are we going to get if we do that? Well, to simplify this, let's see what happens if we take n derivatives with respect to x of x to the m. Okay? And well, in this case, also m is bigger than n, because if n is bigger, then well, this will be 0. Okay? So we will get, for example, m times the derivative n minus 1 with respect to x of x to the m minus 1. Okay, and we need to continue taking derivatives again and again. Okay, so we are going to get that this is, for example, m times m minus 1 times n minus 2 all the way up to m minus n plus 1 times x to the m minus n. Look, because we are taking n derivatives, we need to subtract n times 1 in this exponent. Okay, so we are going to subtract n from m in the exponent of the x, and we are taking these terms one more than the exponent of the x. Okay, so this is what we are going to get. This will be the nth derivative with respect to x of x to the m. But look that, well, this is very similar to the term m factorial. What is m factorial? It will be m times m minus 1 times m minus 2 all the way up to m minus n plus 1 times m minus n factorial. Okay? And then, well, we can say that all this expression that we have here, it's going to be equal to m factorial over m minus n factorial. But that is what we have here. Okay? So we can say that this is equal to m factorial over m minus n factorial, because I take this into the left hand side of the equation. Okay, so we can rewrite this as m factorial over m minus n factorial times x to the m minus n. And remember that we were calculating the derivative with respect to x n times of x to the m. Okay, so what happens if we apply this formula to what we have here? Okay, so the nth derivative with respect to x of x to the 2k, well, in this case m is equal to 2k, and we are going to use the formula that we found. Okay, so this will be 2k factorial over m, which is 2k, minus n factorial times x to the 2k minus n. Okay? So if we substitute that in our formula for Pn of x, we are going to get that Pn of x is equal to 1 over 2 to the n times n factorial times the sum from k equals 0 to infinity of n choose k times negative 1 to the n minus k power, and then all this that we just found. That will be 2k factorial over 2k minus n factorial times x to the 2k minus n. And look that we have an n factorial over here, and we can take it into this expression inside the sum. Okay, if we do that, we are going to get n factorial over here. We take it out from here, and let's examine this term. It's very easy to notice that this term is equal to 2k choose n. Okay, so we can say that Pn of x is going to be 1 over 2 to the n times the sum from k equals 0 to infinity of n choose k times 2k choose n times negative 1 to the n minus k power times x to the 2k minus n. Okay, so finally this is going to be a series expansion for Legendre polynomials. This will be the first important result of the video. Okay, like another way to define Legendre polynomials. What we can say is that, well, look that we defined the binomial definition of Newton taking x squared to the k power. Okay, but looking that the sum is commutative, well, we could say that this could be negative 1 and this would be x squared. Okay, so we have a different expression for the binomial formula that will define different this expression over here. So we can just make a similar process with this expression over here, and that will be like a good exercise to do to get another series expansion for Legendre polynomials. It will be similar but different. Okay, the expression that we will get if we do that is going to be this one over here. So this is equivalent to the first definition that we found. Okay, well, this would be the important definitions of the Legendre polynomials as a series expansions. But there are other ways to define Legendre polynomials as a series expansions of infinite sums. What we are going to do right now is to take again the definition of the Legendre polynomials. Let me rewrite this. Okay, and here we are going to look again to this term, and instead of looking at it as a sum of two terms, we are going to look at it as a product. It's very easy to notice that this can be expressed as x plus 1 times x minus 1, okay, raised to the nth power. So we can just split the n here, okay, and we have the nth derivative with respect to x of a product of functions. In this case, let me name this as f and this as g. And the general Leibniz rule says that the nth derivative with respect to x of a product f times g, well, it will be equal to the sum from k equals 0 to infinity of n choose k times the kth derivative with respect to x of f times the n minus kth derivative with respect to x of g. Okay, so if we use this formula, we want to calculate this term, we are going to substitute f here. So we are going to get that the nth derivative with respect to x of x plus 1 to the n times x minus 1 to the n is going to be the sum from k equals 0 to infinity of n choose k times kth derivative with respect to x of x plus 1 to the n power, and then the n minus kth derivative with respect to x of x minus 1 to the n power. Okay, so we are going to calculate these two terms that we have here. Okay, it will be very similar to what we have done on the first step of the video. So the kth derivative with respect to x of x plus 1 to the n power, it will be, well, n times n minus 1 times n minus 2 all the way up to n minus k plus 1 times x plus 1 to the n minus k. Okay, making a similar process to what we done on the first expansion of the video. So again, we can say that n factorial is equal to n times n minus 1 all the way up to n minus k plus 1 times n minus k factorial. So all this is going to be equal to n factorial over n minus k factorial. So this is going to be equal to n factorial over n minus k factorial times x plus 1 to the n minus kth power. Okay, so that will be this term that we have here. So what happens with the second term? We are going to have the n minus kth derivative with respect to x of x minus 1 to the n power. Okay, so if we develop this, we are going to have n times n minus 1 all the way up to, well, it will be n minus the order of the derivative, that is n minus k plus 1 times x minus 1 times, to the n minus k power. And this will be equal to n times n minus 1 all the way up to k plus 1 times x minus 1 to the kth power. And again, we see that n factorial is equal to n times n minus 1 all the way up to k plus 1 times k factorial, and n factorial over k factorial is equal to n times n minus 1 all the way up to k plus 1. So this thing over here can be rewritten as this. So this is going to be equal to n factorial over k factorial times x minus 1 to the kth power. Okay. So we are going to rewrite the definition of the Legendre polynomials. Now with these terms that we just found, we have, remember that this one and this one for the derivatives. Okay? So, okay, we are going to get the Legendre polynomial is going to be equal to 1 over 2 to the n power times n factorial, and, well, the derivative of this product, but that is the sum from k equals 0 to infinity of n choose k, and then the terms that we found. It will be n factorial over n minus k factorial times x plus 1 to the n minus k times the other term, which is n factorial over k factorial times x minus 1 to the kth power. Okay, so let me copy this. Okay, I rewrote the expression for the Legendre polynomials, and we easily see here that we can cancel this n factorial with this n factorial, and we are going to get 1 over 2 to the n times the sum from k equals 0 to infinity. And look at that, this k factorial, we can move it here, okay, so we can write this here, and it's easy to notice that this is the definition of the binomial coefficient. This is n choose k. But with this n choose k that we have here, we are going to get n choose k squared. So n choose k squared here, and then x plus 1 to the n minus kth power times x minus 1 to the kth power. And this will be p sub n of x. So again, we have just found another series expansion definition for the Legendre polynomials. Okay, this will be the second important result of the video. And again, it happens something similar to the first example. We used this formula to get the series expansion, okay, but we took the kth derivative over f. And looking that the product is commutative, we could rewrite this instead of writing f, we can say that this is g and this will be f. Okay, so if we do that, we are going to get a similar result, but not exactly the same. And again, that will be a good exercise for you to do. If you do that, well, you are going to get the next result. You are going to get this result over here. Look, that is actually very, very similar to what we have done. We just need to switch x minus 1 to here and x plus 1 to here, and we get that. So we would have, in this case, 4 series expansions definitions for the Legendre polynomials. This one, and these two over here. Okay? Okay, so that will be the important results of the video. Feel free to leave any question on the comments, and on next videos we are going to keep examining Legendre polynomials, so as the generating function for the Legendre polynomials and some recursive definitions for this that will be very useful in, for example, in the study of electrostatics. Okay, Legendre polynomials appear in electromagnetism, in electric multiples, for example, so we are going to be making videos about these topics.